Hello, good evening to everyone in Sri Lanka and also good evening to Matt. And also, based on your location, maybe good morning or good afternoon. And as the chair of the IEEE CAS SEDA Sri Lankan chapter, I would like to welcome Matt Venn, a leading voice in open source IC design as a guest speaker. And also, I would like to welcome all the attendees to this session. And since we are a little bit late, so the I would give my brief introduction to brief, and I would like to invite Mr. Kitmin Randula, who organized this session, to briefly introduce Matt Ben. Thanks.
Thank you, Dr. Shamira. Yes, I would. It's my pleasure to invite Matt Venn to conduct today's webinar on current and future opportunities available in open source IC design. Matt Venn is an electronic engineer, science communicator, and leading voice in the open source Silicon movement. He is the creator of the popular Zero to ASIC course, which is one of the most famous training courses, which empowers enthusiasts and engineers to design their own chips. And he's also the founder of Tiny Tapeout, one of the most revolutionary and valuable platforms that has enabled hundreds of community source designs to be manufactured on shared silicon wafers, and actually something that has allowed Sri Lanka to actually design our own first ever tape outs. And thank you, Matt, for accepting the invitation today. It's really great to have you. Yeah, over to you.
Yes, thanks for the invitation. I've got some slides here, obviously. And I will share a link to the slides at the end of this presentation.
Awesome. Thank you so much.
Okay, thank you. Great.
All right. I'm just trying to also find the chat. Okay. So I'd like to get started actually by asking all of you a question. Maybe you can just start off by what's an easy thing to do on the chats? Like do a smiley face in the chat depending on how you're feeling right now. Cool. Okay, and give me a thumbs up if you've ever done a digital design before. With it for either simulation, FPGA. And give me a thumbs up if you've done a tape out on an ASIC before. Kivmin has. Give me a smiley with heart eyes if you've done a tiny tape out before. Okay, so we've got plenty of Ricardo gives me a thumbs down. We've got plenty of opportunities, and that's one of the things I want to be talking about, to do affordable tape outs. And one of the reasons why I really wanted to make Tiny Tape Out and to come and talk to you today was to show that it's more accessible than ever to get your designs onto silicon. So now that I know a little bit more about you, I'll tell you a little bit about me. I'm a engineer and science communicator. This is a big robot that I built for a science museum in England, and it was connected to their solar panels. And every 5 minutes, it would come and draw a leaf. And then, depending on the size of the leaf, would be how much energy had been generated from the solar panels. This was a competition I made that was to see who can build the car that goes the furthest on some hydrogen. That was called the Fuel Cell Challenge. And that workshop is still running, and it's had, I think, maybe 20,000 people take part in it now. And this is a keyboard that I made where we sold any volume. I think this keyboard has sold 25,000 units now, and I'm actually on the next version, so I'm no longer in the company, but this is the new version which I've got on my desk. So that's my daily driver. And I only really got into FPGAs, I don't know, about 7 or 8 years ago, as part of my science communication, as part of my electronic engineering side of things, when I finally had a project that needed very accurate timing. And one of the things that I found inspiring at the time was this a photo from an event, an O'Reilly event. Being new at something and bad at it. And at the time, I was still very, I needed to be good at things. I felt like bad if I felt ashamed or bad if I wasn't good at something. And I was afraid to share my progress if I wasn't good. But that kind of started changing for me. And this was, I think, one of the things that helped free myself from that, which I think is quite a limiting way of uh, going through life. It's fine to be bad at something. Every time we start something new, we're going to be bad at it. And it's great. It's a joy to be able to start something new and be bad at it. So if you've never done any silicon or FPGA or ASIC stuff, don't worry about being bad at it to start with. Um, Use the opportunity to find a mentor, start a project, um, present your project, study other people's work, and then eventually start teaching. And that's what I did. And eventually, 10 years later, that led to the Zero to ASIC course. So a little bit of history on open source silicon. We've had open source PDKs. Just give me a thumbs up in the chat if you know what a PDK is. We've had open source PDKs for many years, but they've been non-manufacturable. So they're useful for learning, they're useful for education, but you can't take anything that you've made with an academic open source PDK and actually tape it out. So I've got 4 people in the chat put their thumbs up. So a PDK is a big database of files that helps you to make and design a chip that is manufacturable in a particular factory. So every factory has its own PDK, and in the PDK will be information like how close together you can draw wires. If you draw the wires too close, their machines aren't going to be able to make it. A library of all the logic cells that are available. Maybe some standardized IP like memory and SRAM, stuff like this. So there'd been many open source PDKs, but none of them manufacturable, and that all changed in 2020. And at the same time, Tir Mansell, who announced that, also made a system so that if you submitted an open source design, it could get manufactured free of charge. And that was a game changer for me because I had experimented with the open source tools, made a GDS file, and then realized it was going to cost like $15,000 to actually make any chips. So I kind of stopped my research and exploration on that. But then with the advent of the open source and free tapeout, I had adapted one of my projects to use an FPGA project to use the new PDK and was able to get the GDS ready for tape out. I did a presentation about that in November for Hackaday, and then we had the first free tape out with the Fabulous in December. And I realized that there was a lot of room inside the chip, so I collaborated with a bunch of other people. So a lot of these projects are mine, but I also collaborated with 4 or 5 other people to put other projects on. And this was my first exploration of putting multiple designs onto one chip. And I'd like to say thanks to Maximo for the lovely photo and Texplained for the die images. So the idea of the open source and sponsored MPWs was to try to get more people involved, and especially people that haven't had the opportunity to do tape outs before. There was 40 slots per tape out, and in the end there was about 10 tape outs overall, and I had chips on almost all of them. Oh, I've got the wrong. I wanted the laser. Following my explorations, I realized there was a lot of interest. So that's when I started the 0 to ASIC course, early 2021. And since then, I've had about 650 people take the course. It took 10 months for us to get the first chips back, which is twice as long as normal. And I guess it's not that surprising because it was a lot of things we were doing first times. But unfortunately, the chips were very difficult to get working because there were some pretty badly broken problems with it. If you want the information on there, you can check this link here. But the short version is the tools weren't set up correctly and a hold violation wasn't detected. For my course, I started getting a bit more organized. So I built some tools that could put together 16 designs. Still a lot of wasted space you can see here. But the first 16 people on the course, we collaborated, we made a chip, we got all these designs together on there, and I used a tri-state bus to connect them all together. And the highlighted wires here you can see are the enable lines. So when the enable goes high, the design turns on. And by the way, feel free to drop questions in the chat. So yes, it was pretty difficult getting those first chips ready, but I was able to get most of them working. It was pretty complicated. With enough fiddling around, you could get some outputs to work, and then with enough other fiddling around, you could get other outputs to work. So you could kind of do 2 tests and check that you got all the outputs working. So for my 7-segment display driver, like one of the segments was always off. And for my clock, I never got the full red color because I couldn't drive both red outputs at once. But it was amazing to have chips in hand that were my first chips and to get them working. So continued 2022. We had MPW2 out of the fab. And in June, we taped out MPW6. And on MPW7 was my first attempt at Tiny Tapeout. So this was putting 500 very tiny designs onto one chip. After MPW6, all the chips working fine. So up to MPW5 was difficult to get working. Everything after MPW6 worked fine. A bunch of changes were made by eFabless. But then in 2023, we were expecting an April shuttle, which never happened, which was bad news. Um, we got Tiny Tapeout 2 in January 2023, and we finally got that working in October, which was amazing. We did that on a live stream, which I think was the world's first public live bring up of a chip. Most people do that in secret. But like what I said, be new at something and be bad at it. It's like no one wants to admit that they messed up their chip and it doesn't work. And I think it's a really important thing to kind of change the attitude to that as um, part of my philosophy. Kithmin says, how do we handle the chip wire bonding packaging? The early chips were these ones. They were called wafer level chip scale package. So they were bumped dies. You can kind of see here in this photo. They're like little BGAs. They were hard to handle, but not impossible. We did some wire bonding later, but we didn't have to do it at the beginning. Okay, around about this time also was I got an opportunity to take my first chip into a advanced light source. This was in Switzerland. Put it in this incredible machine and then do X-ray tachometry on it, which let me get a 3D image of my chip so I could look right down inside. And this is a view of looking inside one of my early chips. Like I said, MPW 2 and 3 and 4, we all got them like partially working, but they all had the same problem with the pad frame. That's the problem with the long delay on the tape out, is if you have a problem in there, you don't spot it for ages. 24, we had the first analog designs in Tiny Tape. Launched my 0 to ASIC analog course. We had the Z80 go out of manufacture and an open source Z80. The Tiny Tapeout demo scene. Play you my favorite entry. I don't know if the sound is going to work here. Give me a thumbs up if you can hear the sound. No sounds. Oh well. Hopefully the graphics are pretty cool anyway, aren't they? So I'll paste the link here, but you can check the sound out later when I share the slides. Whoops. But that was a great competition. And then we did our first IHP test chips in October. And then we had the very bad news earlier this year of eFabless going out of business in March. But two of the founder members restarted a company called Chip Foundry, which we're continuing to collaborate with. And we've just started working with global foundries. So this is kind of where we are now. And I'll talk more about the foundry situation later. I just wanted to give a quick intro. So one of the great things about the open source tools, let me get the chat open again, is we see a lot of people making very interesting tools. So this is an example of somebody making their own tool based on what we've done, what the open source community have done. And this is simulating the gate level netlist of an ASIC design in the browser. And I can increase the speed here. And this design plugs into a computer screen, and what you're seeing up here in the top is what is going to get output onto the computer screen. top right is the clock divider and generating the H-sync and V-sync for the monitor. And as the design progresses, we get to see this cool fractal getting output in the top left-hand corner. And what's also really amazing is that this is a 3D design, so you can kind of check it out from different angles and even zoom into it and explore the design working. So I think it really gives a nice insight into how things work at that fundamental level. And this is a good opportunity for the community for open source EDA, is that you can build your own tools. And we can create tools that haven't been thought of by the industry standard tools. We just my computer is very slow for some reason. I don't know what is going on there. And another tool is our new chip viewer. So we're working with a company called TechSplain to do reverse engineering, and they can do this great imaging. And we've combined the GDS layout of Tiny Tapeout designs with the microscope view as well. And also being able to turn on the project link. So if you find a cool project, you can click on it and then get all the information about that design, whether it's been tested, open it in the 3D viewer and so on. So there's a lot of opportunity to be involved in maintaining the tools, testing the cool tools, contributing to the tools, creating your own tools. But I think for me, one of the things that makes me excited about the open source silicon world is actually being able to create designs and get them manufactured. So I'm going to give you a quick overview of where we're at with fab status. So we have a collaboration with IHP, which is a German fab. They also have an open source PDK, and we've got a shuttle open with them at the moment. This is our first test chip with them, which works. That was really cool. Bit of wire bonding there, I mentioned earlier. Nice to get packaged parts and not have to wire bond them. We are working with Chip Foundry to keep access to Sky 130. And right now we have Sky 130 open, and it's got another 20 days left. There's still plenty of room. This is the chip map at the moment, and I'll mention a few more details about that in a bit. And we just got some funding from a company called Tilitus, who does security keys, physical security keys. And they are funding development work in Global Foundries. So Global Foundries is an interesting PDK, another open source PDK. And we're hoping that with Global Foundries, we'll be able to get much faster chips back and also cheaper, which I think is also important. So, like I mentioned, I've only really been working on with ASICs for 4 or 5 years. I'm still a beginner in a lot of ways. Most of the work that I do is on teaching, so I don't do like really complicated or crazy designs. I'm more working on designs to help other people learn. So I'm always wanting to talk to other experts, and Dr. Carsten Wolf is the principal IC scientist at Nordic Semi, one of the successful European semiconductor companies. And he's been using the open source tools and doing tape outs. He just did another tape out on our Sky Shuttle. And he is a believer in the use of open source tools. He thinks it's just a matter of time. If you want to watch my interview with him, you can check that YouTube video there. Now, another opportunity that people often ask me about is wanting to get internships. And I asked a couple of people who are involved in open source tools and work in industry, Thomas Parry at Spherical and Carsten, this guy I just mentioned at Nordic, and this is what their responses were. So they suggested doing custom peripherals that can integrate into a RISC-V project, demonstrating creating a block and integrating into IP. And Carsten had a chat with his digital guys at Nordic, and again, they kind of came up on the idea of making a peripheral for a RISC-V processor that could work over SPI. So that's some ideas on projects that you could do with Verilog, simulate them on an FPGA, tape them out on Tiny Tapeout, and that would be a good thing to have on your CV to help you get an internship at one of these companies. Another opportunity is the IEEE Society competitions. So I'm a member of the Solid State Circuits Society, and we have yearly collaborations and competitions. One's called the PICO program, one's called CoderChip. There's also travel grants and things like that. And you can enter these as a group of people and work on some really interesting designs. And I have started hiring people who I thought did a good job on previous competitions. So most of you are probably going to want to find work and opportunities with existing larger semiconductor companies. And they can often be very picky about you need to have done this kind of stuff, have experience with those kinds of tools and so on. But I think as more people are using the open source tools to design products and to do research, there's going to be more jobs available for people that don't have all the traditional things that are needed by these big companies. So I just asked 3 or 4 people to make me a proposal for some custom analog IP that I wanted to build. And then I picked the one that I felt was the best proposal. And now I'm paying this guy to do this work for me, and he's publishing it all open source. So that's another thing you can do. Enter one of these competitions, get some skills, get some feedback, and maybe one day in the future, I'll hire you. So another bit of input from this time an anonymous engineer who works at Apple. And he says that one of the things that he likes most about the open source tools is it makes self-study much more possible. So you can, even if you're not getting access to Cadence or Synopsys tools, you can still learn all the fundamentals of things like timing analysis and how flip-flops work and digital logic and analog layout. You can get all the fundamentals with the open source tools. And he thinks that open source EDA is going to be key to making VLSI accessible for more students. So it's a growing community. We just lost the Slack, unfortunately, because that was a paid-for program by eFabless. And now eFabless is out of business. No one's paying for it. So we've moved over to fossychat.org. So I'd recommend that you join there. We've got also 3,000 people on the Tiny Tapeout Discord. And we've got these other PDKs be available and available soon. So moving on to Tiny Tapeout. We've got about 5,000 people involved. Like I said, 3,000 on the Discord, about 5,000 on the mailing list. Altogether, they have worked to contribute 1,500 designs, 100 of which have been silicon proven. And we worked with 50 universities in 30 countries to make 10 chips. And these are a couple of the chips I'm most happy with because they're most full of designs. We do these in-person workshops, and this was a recent one. So it's really incredible to be able to do a 4-hour tape out workshop where everybody gets to do a tape out just in one day. And that's only possible with the open source tools. And here's another couple of quotes. One from Jörn, who used to be like a traditional industry standard guy, but now is working freelance with the open source tools. And one is with my analog mentor, Harold Prettel, giving their opinion on Tiny Tapeout. So talking of analog, Kitmin is saying, do you think there's an industry demand for open source analog IPs? Yes, I think there is. I think that when people ask me about making products with open source EDA tools, I don't think we're really ready for that because we don't have enough of the fundamental analog IP like D2As and A to Ds and band gaps and regulators and all this important stuff you need. And it takes a long time to design, and it also takes a long time to validate and show that it works properly. So it's a very big opportunity and is still a big hole that is slowly being filled. So I want to show you a quick demo of Tiny Tapeout, and we're going to end up showing it working on one of these demo boards. So this is a very simple design that was taped out in one of our workshops. And for very simple digital logic, if you're a complete beginner or you're working with complete beginners, I really recommend using a schematic editor like this because it's a lot less confusing than Verilog. And we can simulate this. So let's take a look at the first two inputs. They come in here, they go up to this AND gate, and then out on output 0. So if I turn on this one and this one, we see this LED turn on. And then let me also enable the clock, which will run through this chain of flip-flops here. So now we see these LEDs blinking. This one is blinking fast and this one is blinking slow. So after we've got our design in Wokwi, we can create the workflow with a GitHub repository. So it's very simple to start with. All you've got to do is take this number from up here and paste it in here, write a bit of documentation and describe what the pinout should be so that we have this for the documentation. And then once you commit, it runs a GitHub action, which automatically installs the PDK. And then LibreLane, that's the new name for OpenLane, and tells us how many cells it needed. So we saw we've got 16 of these flip-flops. And here we see we've got 16 flip-flops. I can click on that. I can see what the layout is on the GDS. I can see my top level view, and I can open the 3D viewer. Can turn off the fill cells. So this is quite an empty design. Turn off the routing, and these big cells are the flip-flops that we just saw in the PDK. And we can see all the way down to the MOSFETs. So we've got a real great view of how all this stuff comes together. Then once that is ready, we can submit it to Tiny Tapeout. So this was submitted onto Tiny Tapeout 5. If I just go back here, we can see it's this design here. So along with all the other designs submitted, that one there is the one that we've just taken a look at. And then I can load up that design with the commander. Let me just grab a board. So there's the board there, and I can connect to it. Yeah, I can search for the designs here and enable it. So if you look at the bottom left-hand corner, those LEDs change now, and I can interact with it. So if I turn on input 0 and input 1, we get that top first LED turning on. And if I enable the clock, we see the LEDs starting to flash as well. So the whole system is very easy to use and to tape out, and then easy to bring up and test once you've got the results back. So that's a very simple project. Let's take a look at a couple more advanced projects. I mentioned the open source Z80 that was taped out and has been validated. 12-bit A to Z. I really like the way this one looks. And one of the new features we've added to the 3D viewer is being able to separate out all the layers. And got this auto rotation and black and white mode, which I think looks super cool. Sylvain Minot used two Tiny Tapeout boards to build a software-defined radio. He was using an ADC on one and a mixer on the other. So between the two of them, you can build an SDR. We got a Linux-capable RISC-V on Tiny Tapeout 6 that you can log into and interact with through the serial port. A really nice, well-featured microcontroller with incredible documentation. One of the amazing things about Tiny Tapeout is if you submit a design, you're not just going to get your design, you're going to get everybody else's design as well. So if you do a good job on your documentation, it's more likely that people are going to test it, and then you're going to get feedback that your design is silicon proven. 555 timer, which I tested recently, and it was really cool to see the classic analog waveforms as the 555 timer worked. And I was able to get it working up to 3 megahertz, which is faster than the stock part. So that was fun. And we have a list of all the designs that have been tested. So if you get a board, you can come here and say, let's see which are the ones that have been tested on Tiny Tapeout 6. These are all the silicon proven designs. And then you could pick one that hasn't been tested and contribute by doing a test. So another super exciting project that we've just done is Tiny Tapeout in space. So we're collaborating with a university in Europe. We're putting our chip on their CubeSat, and then we're going to be able to run experiments on those designs. So that's Tiny Tapeout 6. So all the people that had a design on Tiny Tapeout 6 had an opportunity to also test their design in space. And depending how that goes, that's something that we'll consider doing on future shuttles as well. There you can see our chip here, along with 4 other projects. So when this goes up, it cuts a wire, the solar panels open, and the all the designs get flipped out on this kind of big board at the end here. Udara says, are there fabless companies who've also already commercialized chips using open source tools? I would guess definitely yes, but they don't like to tell us about it. Um, CocoaTB is an open source Python framework for chip testing and digital design testing, and that's used by a lot of big companies, including IBM. Um, and but it's not something that they really boast about. Um, Now, it's unlikely that the chip is 100% open source. Um, and I think that will happen in time, but I would imagine it's kind of 5 to 10 years out. Yeah, so Kidmin says, got a ASIC research project coming on the Sky 25A. Good job. You've got sent the link here. So you want to make sure that yeah, your docs are looking good. Well, this one's not looking so good. So if you want other people to test it, you need to fill this out. And the better you do that, the more likely it is that people will help test it. Okay, so another opportunity for you is the RISC-V, the crowdsourced RISC-V competition. We're providing a core, a RISC-V core that we've used before, and then other people can, so you can create a peripheral that talks to that RISC-V core and then becomes part of the bigger microcontroller. It's a really good opportunity. It's free to enter. We've got some good prizes and we've got some great judges. So it's an opportunity to have your design seen by somebody like Yuning Liang, who's the CEO and founder of Deep Computing, or Flo, who's the head of Open Hardware Foundation, or Bunny Huang, who I think is one of the best known hardware hackers in the world. And we've already got a whole bunch of peripherals already submitted. Let me see if I can. 40 closed pull requests. So I think there's about 30 different peripherals have already been added to this project. And if we go to Tiny Tapeout Sky, it's this really big one here. So we actually had to enable 4 high designs to be able to fit this design in. It's the biggest Tiny Tapeout design we've ever done so far. So you've got just over a week to enter that competition. Again, it's free of charge to enter, and it's a good opportunity to get your design in front of some very influential RISC-V people. And that's where I'm going to finish up. We can use the rest of the time for any questions. So feel free to grab the slides from here. I just drop the link in there. Connect with me on LinkedIn. Don't just send a connect message though. Don't just do a connect. Send a message as well saying that you were part of the CAS webinar, because I get too many connect requests from people I don't know. Just say that you're on CAS webinar. If you want to find out more about Tiny Tapeout, you can read the paper that was published in the Solid State Circuits magazine. Subscribe to my newsletter. Subscribe to my YouTube channel. and we spend the rest of the time on questions. Thanks very much, everybody, for your attention.
Thank you. Thank you so much, Matt. Yeah, that was an awesome presentation. Yeah, I think I'll open the floor to questions. Feel free to unmute and ask your questions as well. This is a very rare opportunity to interact with Matt. I actually have the first question in the queue, actually. Maybe I'll go ahead first. So in the current like the Sky 130 Tiny Tapeout platform, I've always wondered why there were only like 32 analog slots, but mainly also why it was only like 6 analog pins that was available. Like when we did one of our tape outs last year with Unicast, we saw that like they had allowed around like 20 no like 22 analog pins on the Caraval frame. So I was just wondering why the low amount of analog pins. Was that design decision of some sort?
It's so with I think open frame, there's 40 or 50 pins, and we wanted to have a mix between digital and analog, and the highest number of designs that get submitted are digital.
Okay.
So we reserved 12 for analog. Let me just load up the chip map here. The green muxes are the analog muxes. And each of them goes to 6 pins. So there's 6 pins on this side and 6 pins on this side.
Right. Okay. Right.
And
Right.
we limit the number of total analog designs because we have to mux the pins together. So the more muxes there are, the more of a parasitic capacitive load there is on the analog line.
Right. Okay.
So we limit the pins because we want to have a mix of digital and analog, and we limit the number of designs because we don't want the analog performance to be too degraded. And that's also why we charge money for the pins so that people only use the pins if they need to. So we get the best performance that we can.
Oh, okay. Yeah.
If they were
Right.
if they were kind of like free to use, and people would probably use them all, and then every pin would have the maximum loading.
Yeah. That makes sense. Um, and are there any like platforms that will allow more analog pins in the future? And maybe like in IHP, some of the tape outs we did, we were allowed to have our own um, pads and like seal ring and
Mm.
that kind of
I think it's
um,
probably unlikely with Tiny Tapeout because we're trying to be fairly generic and appealing to beginners and amateurs. And once you start doing custom pad frames, you're best off just doing your own custom chip, everything totally custom.
okay. Yeah. There is a question in the chat as well. Are there any RISC-V related projects, probably like associated with Tiny Tapeout, that might be like interesting to work on? I think there is certainly one I think you shared earlier. I can actually find the link for that as well.
I'm not 100% sure I understand this question from Tashin. Um, RISC-V projects which will be related with ASIC. Does that mean risk RISC-V projects on Tiny Tapeout, or RISC-V projects that are only for ASIC? Yeah, I'm not. Maybe Tashin, if that's not a good answer, then you could clarify. RISC-V with Tiny. Yeah, there's the search on Tiny Tapeout works quite well. So if you go to Tiny Tapeout and type in risk or risk 5. Um, you get quite a lot of stuff here. So like on, if we go to here, so we've got Michael Bell's Tiny QV. We've got a risk 5 32i core, and we've got this was also the one with the Cayenne 5 that you posted as well. That's also risk 5. So yeah, it's quite popular. I would say probably maybe 15 or 20 risk 5 micro CPUs have been taped out with Tiny Tapeout so far. Any other questions in the last 5 minutes?
Yeah, it doesn't seem to be
Okay.
prohibiting anyone. I think we can maybe conclude today's webinar. Dr. Shamira.
Yeah, actually, so the thank you very much, Matt, for very interesting webinar, and I think this would be really instrumental for the enhancing the interest and the enlightening the students in countries like Sri Lanka and other areas where the ASIC design and taping out is very rare. And also, I would like to actually thank you and greatly appreciate your interest. And also, basically, this open initiative, open IC initiative, and that's tremendous. And I do not have any words to explain further. Thank you very much. And also, thank you very much for accepting our invitation as well. So, thanks again.
You're welcome. Nice to be here. And
Great.
I really hope to visit one day. I'd really love to come and visit Sri Lanka.
Yeah, we would
You are
really love to
always
have you
welcome.
as well.
Yes.
Thank you. Thank you so much, Matt. And thank you
Okay,
everyone
well,
for attending today's webinar.
have a good evening, everybody, and hope to see some of your designs on a future Tiny Tape Out, and maybe even on this Risk 5 competition.
Thank
Yes.
you.
Yes. Thank you so much.
Bye bye, everyone.
Okay. Bye. Bye.